let us introduce to a scalar quantity called potential. So we have seen the conservative force field. In a conservative force field, the work done is independent of path. So in a conservative force field, the work done is independent of path. So since in a conservative force field the work done is independent of path, so we can define a scalar function, a scalar quantity to each and every point such that the difference of which gives the work done in moving from one point to other. So you see, what is our idea? This is point A, this is point B. So if I select any of the path and the work done is same for all the paths, so if work done from A to B by path 1 is A to B equal to path 2 is equal to A to B for path C, then why not define a work done from A to B as something which is the difference of B and A. So the difference of B and A will be giving the work done. That means whenever we have a conservative force field, we can define a scalar quantity to each and every point. This scalar function is called potential. So thus, what is a potential? So the potential is to every conservative force field we can define a scalar function called potential such that the difference of which gives the work done. So in that way, another property of the conservative force field is that we can define a scalar function for it. So very important point. Thus a conservative force field is also called potential field. So this is also called a potential field. To every associated conservative vector field, we have a scalar potential field. So thus we have defined a quantity called potential, which is a scalar quantity and which is capable of telling the properties of the vector field. Now we see here, very important point, we don't define the potential at a point A or potential at a point B. Basically, we define the potential difference between A and B, which is the work done. So very important point here I am writing. We actually actually does not define the potential at a point, but we define the potential difference between 2 points, which is the work done between the 2 points. So potential is not actually defined, but potential difference is defined. We see that we don't define potential, but actually potential difference. So you see, I have 2 points A and B. So what is the idea of defining potential? Suppose I say the potential at point A is something. Suppose I say some mathematical number, I give 2 plus 3i. So this is a mathematical number and it has no physical meaning. And here I say it is 3 plus 3i. So you see, I can assign any value to A and B. Whether it is a meaningful value or not, doesn't matter. But what should matter is the difference. That is, suppose I say I want the difference UB minus UA, that must be, that is 3 plus 3i minus 2 minus 3i. So that becomes 1. That 1 should be the work done from A to B. That means my individual potentials may be defined, may not be defined, but that difference is always defined. So we don't define potential, but we define the potential difference. Now let us define the potential at a point with the help of the potential difference. So what we will do? So now our task is to define the potential at a point. So potential at a point is defined with the help of a reference point. Suppose I am defining the potential at A, potential at B, potential at C, then I will select a reference point, then I will do some work from here to here, then I will say the work done from R to A is the potential UA, work done from R to B is the potential of B, work done from here to here, this is the potential at C. So in this way, let us define potential. That means again I am using the idea of potential difference to define the potential of a point. So let us see how we define potential. So the potential at a point is defined as the work done by the external agency. Work done by the external agency in bringing a unit. So if the field is gravitational field, I need to bring mass. If the field is electrostatic field, I have to bring the charge. If it is magnetic field, I have to bring the magnetic monopole. So depending on the quantity which interacts with the field, I have to select. So I am writing a unit entity. Entity means the quantity which is interacting with the field. So work done by the external agency in bringing a unit identity from a fixed reference point to the point of intention. Generally the fixed reference point is taken as infinity. Remember, but not always. So, but not always. So that means you are free to select your reference point. There is no binding. Generally, we take it at infinity in gravitation, in electrostatics, in magnetostatics, but not general. Now, so you see the potential, suppose I say potential, I write the potential function as V. So, potential at a point R is defined as work done by external agency F dot dx or dr vector from the fixed reference point to the point R. This is the expression for potential, but we say external, but we express this F external. So since it is to be moved slowly, so we have to always apply external force as against the conservative force. This is conservative, C-O-N, conservative force. That means the definition of potential at a point becomes minus F conservative dot dr from the fixed reference point to the point of intention R. So this is the definition of potential. Now this definition of potential uses the idea that potential is not defined but the potential difference is defined, and I have selected a reference point to define the potential of all the points. Now with this definition, now I talk the potential difference between these 2 points. Now let us define the potential difference between these 2 points. So potential difference between A and B is given by, this is UA minus UB. Suppose I am taking UA minus UB. So UA is minus reference point to A, F dot dr. This is one quantity, that is UA, minus UB means minus R to B, F dot dr. So these are 2 quantities. So we have UA minus UB or VA minus VB. The limits will change the sign, A to R, F dot dr. Again it will be plus R to B, F dot dr. So this A to R then R to B becomes A to B, F dot dr. So now you see here, this is F is the conservative force, and we write this as VA minus VB as minus F dot dr from B to A. So this is the general expression for the potential difference between 2 points. VA minus VB is minus B to A, F dot dr. You remember F is the conservative force, F con. Now let us see force as the negative of gradient of potential. Now generally it is very difficult to calculate force. It is easy to calculate force from potential. So let us see how it can happen. So now let us consider a potential which varies along x axis. So this is our x axis, and consider a conservative force field F, for which we have a scalar function V which varies with x. So presently I am interested in x. So when I say V varies with x, means V is not constant along x. It may be varying along y and z. So presently V varies along x. So I will use the definition of potential VA minus VB as minus B to A F conservative dot dr. So here let we select a point called A and this point as B. So this distance is x and this is x plus dx. So this is very highly exaggerated diagram. This distance is very small compared to x. Dx is very small compared to x. So let A and B be closely spaced points on x-axis. They are so close that we can safely assume fx to be constant over A to B, means they are very close. So I have written dx. The distance between A and B is dx. So we use this VA. VA means V at x minus V at x plus dx is equal to minus. You see this f is constant. So fx into dx and b means x plus dx to dx. So this fx is assumed to be constant. So I will assume this, I can bring this minus here, fx constant, and so this is dx minus x minus dx, so it will become dx. So this will become plus dx. So this minus will go because this is dx minus x minus dx, so minus will go out. Again you see this is Vx plus dx, I write here, minus Vx gives minus fx dx. So you see generally this Vx plus dx minus Vx is written as dv minus fx then dx. So we can write this. So this popular form is, this is change in potential. Change in potential is equal to negative of work done by conservative force. So why we say change in potential is the work done by conservative force. We will write that fx is equal to minus dv by dx. Fx is equal to minus dv by dx. Now you see here, if v varies with y and z, then we have fx is equal to minus dou v by dou x, fy is equal to minus dou v by dou y, and fz is equal to minus dou v by dou z. We write this as f is equal to minus dou v by dou x, I minus dou v by dou yj minus dou v by dou zk. This is in popular form written as minus gradient of v. This is the potential, and we say thus force is the negative of gradient of potential. So you see here, once potential is known, I can calculate the vector field. So I said sometimes calculation of vector field is done through reverse. That means if I know the potential, then I take the gradient of that potential field, that is the conservative field F. So the force is the negative of gradient of potential.